Welcome, everybody. I'd like to introduce Alexander Nasonov to you, and he's going to talk about just-in-time code generator inside the NetBSD kernel, something we don't even have for all architectures in Firefox.
Okay, hi. So yeah, I'm Alex, and sorry, I'm going to sit during my talk because I have a slight problem with my leg. Yeah, it's going mostly to be a talk about development this feature, so it's mostly for developers. But even though it's inside the kernel, there is it's not. I will show you not only C code, but I also show you Lua code, which can run in the kernel, and it just brings new possibilities. And I only started doing Lua while preparing for this talk, because I needed some graphs, and the easiest way is to generate graphs rather than draw them manually. And I've got quite a few of them. So let's start. So this project started near the Christmas time, and before Christmas I did some research, and I made a decision to start working on the project on the 26th of December, and I created a repository on GitHub. It's still there, but at the moment it's it's postponed till next March. But I'm working. I switched to NetBSD 3, and I like 1 year later I added the code to NetBSD 3. But it was just the beginning. Since then I did a couple of more iterations, including some extensions to BPF language for our new packet filter by requests from mid-August. And yeah, it's still work in progress. And I just, while preparing for the presentation, I just discovered how cool it is to use Lua, and I'm going to switch, at least for prototyping, I'm going to switch to Lua. You'll see. So yeah, I'll start with just basic. I assume everyone understands what BPF is. And to enable JIT, you just need in a modular kernel. Like if you run Intel, then it's most likely a modular kernel, unless you compiled a monolithic kernel yourself. And you just need to load BPF module, which automatically loads SLJIT module. SLJIT is the library which I use for code generation. I'll talk about it in a moment. And then you just enable JIT through CTL. Tool, and for monolithic kernel you need to compile with SLJIT option and bpfjit option, and also after you compile you also need to turn it on. And to use it you just need type TCP Dump, then your filter program, and then you can check whether it's compiled or not. Just use fstart and grep for JIT, and if you see a line, then you have your program running in the kernel is JITed. And one thing to note here is this: you can turn on and off BPF at any time, but it doesn't affect running programs. If you had some programs not compiled, then they will not be compiled when you turn on the JIT. They will continue running interpreted. Until you restart, just if you stop TCP dump and start again, it will be compiled. So why I'm doing this? Well, first of all, it was for fun, and there are some implementations in other operating systems, and I thought, it would be nice to catch up and have our own JIT BPF interpreter. Oh, sorry, not interpreter, the compiler. Actually, this slide is supposed to be to show line by line, but I didn't manage to do it. Yeah, good news. BPF is fast because BPF interpreter is fast because it's small, compact interpreter, and but JIT compile is several times fast. I didn't do a lot of performance measurements. It's clear that the compiled code is faster, and for a short program, I tested 1 or 2 programs. For one particular short program, it was 4 times faster, roughly 4 times faster on my AMD box and on ARM. AMD was running NetBSD, ARM was on Linux, because when I started, I used NetBSD at home and used my ARM Chromebook for like just. And I mostly did coding on the train using my ARM Chromebook. But unfortunately, it was Linux. Well, not unfortunately, because I maintained platform independent, not independent, but just it works on Linux and yeah, it worked on Linux and NetBSD, and I'm pretty sure it should be straightforward to port it to FreeBSD. And yeah, it was actually mostly user space, but I later just adapted it to kernel space. Yeah, and there is because I'm using SLJIT library, and I'll describe what SLJIT library is, but it has a small overhead, especially for short programs. I think most overhead is in a prologue, epilogue of functions. So it needs to save some registers when you call a generated function. So yeah, they have a special kind of ABI for calling, or just to pass in arguments and all this stuff. So yeah, I'll briefly discuss what BPF is. I'm pretty sure everyone is familiar with this. So basically, it's a raw interface to the kernel to do packet filtering in the kernel. And it comes with compact machine language for not for real hardware, but for some virtual machine. And it's very simple. And it's usually wrapped. Well, it's wrapped in pcap library, and this is what people normally use. But you don't have to use it. You could send directly to the BPF device. So when you do TCP dump, it compiles the program from the high-level filter language to low-level machine language, and it sends this to the kernel through the raw interface. And it's usually interpreted in the kernel, but it can be compiled. So yeah, as I said, it's very simple. Outside, it looks like a function in written in a special assembly, which you call, and it has a single entry. It doesn't do nested calls, and it has no side effect. You just what you get back is the return value, which is unsigned, a 32-bit unsigned integer. So it has two registers, A and X. A is the main register, X is auxiliary, I think, register, but sometimes it's used. And it comes with a small stack, 16 32-bit memory words. And has simple instructions like add, multiply, bit operations. Yeah, they have one exception because it was original BPF is interpreted, and they thought if they combine two operations, two operations, then they would get a speed up for some very common operation. So there are no backward jumps. It always jumps forwards, and therefore there are no loops. This was made for security, for security purpose, because you don't want to hand your system from user space. So no matter what, it should finish in finite number of steps. And there is also a limit of how long your program can be. So yeah, it indeed finishes in finite number of steps, and it's quite small number of instructions. So you can do, because it's filtering, everything is around loading from a packet, and you can load a byte, a half word, and a 32-bit word. So there are some examples here. Oops. I was going to do something else. So there are index loads. Sometimes you need to load at unknown offset, and you use the X register. So X plus 9 means add the content of X is 9, and just load that offset. And I also asked for, a while ago, I asked to disable wraparound. So I think everyone knows what wraparound is, because for it's unsigned arithmetic, and there is no overflows. There are no overflows. It's modular arithmetic, so that's why I call wraparound. So if you want to do x-1 load at x-1 offset, you cannot do this by just let me try this again. No, it doesn't work. All right. Sorry, I use it for the first time. So, all right. So this one. So you cannot do this because it, just would effectively mean this, and it's not what BPF programs do. They, if they want to achieve the same effect, they would just subtract 1 from x and just load at x offset. Yeah, it has arithmetic operation. Also, by requests of Mindaugas, I added 2 extensions, but these 2 extensions are available only inside the kernel, and they introduce a very significant change to the, at least to the compiler, because those coprocessor functions and external memory, they both have side effects. So it's not, it's not anymore return value, and that's all you get. So you can modify external memory, or you call external function which can modify something outside of BPF. But this is strictly limited to the kernel, because especially with coprocessor functions, you can do a lot of stuff. If you do it from user space, you can break stuff easily. Okay, let's take. I'm not sure. It's not very visible, I'm afraid. And I have bigger. This is the smallest filter program. So basically, it starts by. Let me check if it. No. Just trying to understand, maybe I can zoom in. No, that's not okay. So basically here it loads at offset 12, half byte at offset 12, and then it does a comparison here. First of all, it's for TCPIP, like very simple rule. You want to see IP packets. So you just, this program is very simple. Just check at certain offset, it checks the protocol field and compares with some value. And if it's IP, then it will return this value. You short marks, otherwise it will return 0. And it's very common to the last instruction is return 0, and the one before is return you short marks. Normally, filter programs just either reject all or accept all. And this is, how you say accept or reject all. So, yeah, I forgot to mention that in the round rectangle on the right side, you see a packet length, a minimum packet length you need to be able to load that half word at offset 12. You need 14 a packet of length 14 or more, and if it's shorter, then there is an implicit return 0, and there is always implicit return 0 if your packet is too short. That's and I put 14 in the box. That means you need a packet at least 14 bytes long. So now it's more a bit more complicated filter, which corresponds to ICMP. The thing to note here is there are 2 loads. Let me just switch back again. This one is at offset 14, and this one is at offset. The first one at 12. The second one is 23. Load byte at offset 23, and this is a pattern actually. You see access to packet bytes at increasing offsets, and it's typical because when you go through protocol layers, they usually just go in protocol headers go at increasing offsets. Yeah, that's just often the case, but not always, but often the case, and it actually can help in some for some optimizations. And again, you see this return 0, return you short marks on this slide, and yeah, and this one is again with 2 implicit return 0 checks. Yeah, I think it's even harder. I'm sorry, I don't know how to fix this. Source view. there is. No, I think it always should. Oh, no. Anyway, there is. Oh, maybe actually I can. Yeah, I can do this, but it's not. So this one is for a particular ICMP type, which is ICMP echo request, and just again some like load branch at increasing offset, but not always in increasing offset. Like sometimes it goes. Now I cannot highlight things anymore, and this one has a. Actually, I can just point. This one introduces a new instruction load at indexed offset with indexed by x. And because there is no wraparound, I know the packet should be at least 15 bytes, just 15 bytes here, and somewhere on top you see it actually needs some more than 15, 24. But yeah, the main thing is there are many fallbacks to return 0, both implicit and explicit. These are explicit returns, like basically check the field. It's not what you want, just fallback to return 0. Otherwise, go down the stack or whatever you're doing with your filter, and just until you either reach return 0 or return or accept or reject. Yeah, and this one again with 1, 2, 3, 4, 5 implicit, 5 implicit returns, and oops. And this one actually has 2 checks. One is because x plus 14 can also wrap around. It needs an additional check. So there are actually 2 checks. One is just x plus 14, and the second one is for the result of x plus 14. It should plus 1 byte. This one shouldn't wrap around. So. Because you don't know the value of x in advance. It's, and this actually this is the exception to the simple risk rule of BPF. It's an instruction to quickly load IP header length. Well, it's just p10 with f xf and multiply by 4. Just 2 instructions. Load byte at offset 14 and do just a couple of simple operations. So enough about the filter programs. I'm going to talk more about SLJIT and what it is and how it works. So basically, SLJIT is Stackless JIT Compiler. It's BSD licensed, and it supports multiple architectures. So Intel x86, both in 64 flavor, ARM 3264, several versions of ARM, PowerPC, MIPS, MIPS 64, sparc 32. It doesn't have support for sparc 64 did, and someone did the Tailera port. Everything except Tailera port is written by Zoltan, and I work with him on some new stuff and on improvements. Right. Is it okay? Yeah. Okay, cool. So I'm going to talk about the new work in progress version of SLJIT. Zoltan made a lot of changes, and he renamed registers, he renamed instructions. It just he's like thinking about rethinking about the project and just making changes. So the new version will not be compatible, but once he implements it, at some point I will import it into the NetBSD tree, and I will switch to it. So it's stackless means it doesn't use the stack for temporaries when it emulates instructions. So. And it's kind of it's like an assembler in some strange for some strange architecture, but each assembly instruction is actually API function call. So if you want to generate, if you want to add an instruction to your stream, just make a call, and it has 10 registers, and they are somehow mapped to native registers, but mappings are different on different architectures. There are up to 9 in reality, you have less than up to 10. You have less than 10 registers, less than 10 scratch and less than 10 saved registers. But in total, there are at least 8 registers. They share the same pool of real hardware registers, and they approach from the opposite ends. And some of those registers are emulated, which means they use stack, but to emulate registers. And I think it's only for x86. They don't have enough registers just to. While all other architectures have enough registers to be able to. They have at least 10 registers available from the pool. Yeah, you can also you have access to the stack via SP register like this SLJIT. Okay, actually, constant is just kind of a name of some register, and all registers are named SLJIT underscore R0, so on. And you can also load. Emit an instruction to load the stack pointer into a register of your choice. We can just say, I want a stack pointer in R2, something like this.
So it's Stackless JIT in terms of internal implementation.
Internal implementation.
At the level of its own instruction set provides you with a frame at least.
Yeah. And when you generate a function, you can say, I want this number of bytes available in my stack. And they will be available to you. Yeah, and stackless means for emulating. Sorry, I need some water. Instructions, not registers, because when you write registers, you have no choice. But and for example, it quite often emulates registers. For example, in SLJIT, you can have 3 operand instructions, where destination register is different from 2 source registers, and not all architectures support, and not all instructions support 3 operand, and those will be emulated using additional move instructions. So also SLJIT has labels and jumps, and they are objects, and they will be available as soon as your parent compile object is available, and also. It's JIT, just in time. I think it means not only you can generate on the fly, but also you can patch your code on the fly. So it has some support for changing constants after you generate it. After you generated the code, you can, if you use special flags to mark rewritable jumps and rewritable constants, you can update them on the fly. So yeah, the main register is SLJIT move, this one. Yeah, it can move the data between registers in memory. Yeah, obviously you have load store of different width, byte, half. It's called half. It's not half word because there is word it can be 32-bit or 64-bit, but just half. It means 16-bit and also 32-bit integer, which is called int, and it has the word. Bits, which is either 32-bit on 32-bit platforms or 64-bit on 64-bit platforms, and it has different addressing modes. Like you can load. This means you can load a constant, and actually this constant is not real compiler constant. It's like if you have some function in your C code. And you can pass it to while generating the code. And it will be the constant because it doesn't change while your generated code is executing. So it's constant because you are doing it at runtime, not at link time. So you can also do register plus offset, and you can do register plus offset multiplied by 2, 4, and 8 on 64-bit platforms. So, and also you can do 32-bit mode on 64-bit platforms. And this one is particularly important for bpfjit because all bpfjit stuff, or bpf stuff is 32-bit modular, 32-bit arithmetic. while on 64-bit platforms, on Intel there is RAX, EAX, so you can work with 32-bit numbers, and you need to use this flag, mark your all operations with this flag to make sure they will be as 32-bit. They will be all operations will be 32-bit. 3 operand instructions. I already explained what it is, and they're often emulated. SLJIT has double and single precision floating point. I disabled it in the kernel because we don't normally use floating points in the kernel. And yeah, there's some limitations, and the biggest limitation is you can only call a function, an external function, with up to 3 arguments. If you and this limitation comes from the fact that SLJIT is it works on many platforms, and like limitation of a single platform, just limit all other architectures, because you basically write one code and it runs everywhere. It's not quite correct. You need to you wrote code once, test it twice, and then run it everywhere, because you need to test at least one 32-bit platform and at least one 64-bit platform, and just write once, test twice, and run everywhere. So this is how it worked for me actually. And when I did the first version, I was surprised. There was a bug, and I couldn't run it from the first try. But when I fixed the bug, it worked, and I got home, switched from 32-bit to 64-bit, and again it was mostly working. I fixed 1 more, 2 more bugs, and all was done. There's a special mechanism for doing fast calls, but it's very specific to SLJIT, and I don't use it. And there are some other features I don't use in bpfjit code generator. So yeah, I'm going to give you some example of. Is it still okay to see the? Okay. So this is fast 32-bit division, and this code comes from NetBSD. So NetBSD has this fast divide 32 prepare and fast divide, but fast divide has a bit different prototype. I'll explain it shortly. So basically, it replaces a division by 32-bit division by 64-bit multiplication by a magic number, which is mul, a variable here, and 2 shifts. And the real fast divide in NetBSD is similar to what you see here, but it also passes all these 4 arguments by values in here. And I pass only a single value just because I'm going to show you some assembler, but you will probably not see it because the screen is too small. But it's if I pass this object as globals, it's more easier to compare SLJIT generated code with what the GCC generates. Sorry, this is one. This one is important. It's not C code. It's low code. I wrote it while preparing to the talk, and I think I should zoom it in a little bit. So this Lua code gets called from this. Crazy. No, that's not. So it gets called like this. Anyway. Okay, it gets called from the host C. So this is embedded, and you call it from the C, and from C you pass these 3 integers, and they're accessible as this special syntax for assigning arguments of you received to multiple values. This represents all values passed to your function, and this is a chunk of code, and it's represented as a function. And I think it's quite common in scripting language. Then I create a compiler, and I use chaining. So this syntax means a method. I call a method of this object, and I use chaining. So each method returns the object itself, and it's more convenient how to use chaining. So first of all, I enter a function which accepts one argument, and it uses one saved. Saved means a number of registers which are say, like if this function will not do any function calls, but if a function does a generated function does a function call, this saved registers will be saved after they will have the same value after the call is returns, and you also need saved for arguments, so that always at least like if there is one argument, then there are always at least one saved register. And you need one scratch register. So one saved is S0, this one. One scratch is R0. And yeah, it's a bit messy here. So maybe I can just do this and undo it later. So yeah, it generates just a function prologue, and then you want to. Yeah, I forgot to say on the previous slide, the pattern is you do binary operation followed by a shift and do it 3 times. First one is 64-bit mode. You just use mul. I want to just generate mul multiplication. The destination will be R0 scratch register, and I want to multiply S0 and immediate value mul, which comes from your host C program. And this one is often emulated because it's 3 operand instruction, and then you just shift by 32 immediate value, and the result goes to the same register R0. And this instruction, they're similar, but the main difference is there is I, which means 32-bit mode. So the rest will work in 32-bit mode because you want to 32-bit logic. And the last one, yeah, just very similar, binary operation, shift, binary operation, shift. The last one means I'm returning from this function, so this generates an instruction to return from this function somewhere, and move the content of register I0 to the return register. Well, I0 is always the return register on all SLJIT support architectures, and this means move 32-bit integer, unsigned 32-bit integer. It probably doesn't matter here because when we do initial shift by 32 was 64, just zeroed out high word. Just to demonstrate, you can do this if you want to return, just mask out the high bits and return 32-bit on 64-bit platforms. So that's how much code you need to generate fast division, and this corresponds to real bpfjit instruction. It's not done in my code yet because in C it's quite bigger than this one. I'll show you in a second, and it's division is not very common instruction in BPF programs because it's slow. I think everyone avoids it, and sorry, I need to undo first. Right. And this is how corresponding C code looks like. And it's not all all instructions from the left side. Just about 3, I think. So if you, the first one is create the compiler object, and in C you have error checking. In Lua just throws you, and assuming you run your Lua code in the protected inside the protected call, the C should catch an error and report it somehow. Well, in this case, it shouldn't report any error. You have full control of this code from C, and then the next one. What's wrong? Okay. No. Just the same. All my functions correspond one-to-one to SLJIT, but they don't have SLJIT underscore prefix. And this is essentially the same, except that you can pass the same arguments here. And this is like named arguments. And first 0 is options. It's always 0. It's not present here. This 3 corresponds to this, and these 3 are the same, but for floating point numbers. I don't use any floating point. Floating point registers. I don't use any floating point registers. And also, I check the error. But in SLJIT, you don't have to check an error after each function. You can do it once in a while, and because it will remember your last error. But it's good to detect errors earlier. But it contributes to to the code size quite a bit, and it becomes at some point it becomes unreadable. Just this. This much here, this much here, and also this is for 64-bit platforms because this is using the same width multiplication. On 32-bit platforms, you need double width multiplication because you need 64-bit multiplication here, and it will 32-bit will have a different code, and you need some if here, if else, right? And similarly here, and also there are some special cases like yours. One of these shifts is 0. Or like you divide by power of 2, and at some point it becomes just quite difficult to track, like to understand what's where are you in the code and what's going on, and yeah, it's a bit easier if you do Lua. So yeah, next slide I think. So I will zoom in each code, and I'm going to compare SLJIT with GCC. A bit slow. Right. So this is just the Lua code that corresponds to, just to finish the Lua implementation. So first you push Lua program to the stack, to the Lua stack. It's a single line of code plus 2 lines for error checking, but it basically just loads that Lua code to the Lua stack, and it will be represented as a function, and then pushes three integers, and then it calls the function, that chunk of code you pushed as a function with 3 arguments, and it returns one argument, which is the SLJIT compiler object. And then I'm using my Lua SLJIT library, and you get a pointer to that object from the top of the stack. -1 means get an object from the top of the stack. All objects created inside the Lua are managed by a garbage collector. So if you create multiple objects like jumps, labels, they will all be managed. And if you can use the compiler if you make sure it's somewhere in the Lua stack, so it's available to Lua, it's not dead, then you can use the compiler, and then you can generate code. And when you generate code, you detach your compiler object from the generated code. You can just destroy the compiler object, and because it's managed by the Lua, you can just close the Lua state, and it will deallocate memory for all objects, for all dependent objects. So it's a bit easier to manage once you have the bindings, once you have the library for managing your SLJIT bindings to Lua. Everything happens just manages automatically by Lua, and then you need to free the code some point later. But I'm going to show on the assembler slide. I will show you the content of this function, which is generated on the fly, of course, by SLJIT. Next one is this. You've already seen this, but the pattern is binary operation followed by shift 2 more times. And it's actually, I think, multiplication by residual, scaled residual, with the correction step. That's what it is. And so this is one particular implementation. And on the right side, you see a very simple code for the compiler. And the compiler is not limited to this particular implementation in the middle. It can do, try other alternatives. And it's indeed much shorter. So this one is compiler generated code. It doesn't use this algorithm because it uses a single shift and different magic number. Let me try to zoom in. And real difference here. This is SLJIT code, and it's a bit bigger because the push and just working with stack pointer, not SLJIT stack pointer, just this machine stack pointer. And I think this one is moving our safe register somewhere because it's to save it. And this also has some overhead. Here. And this move actually comes from, remember we returned 32-bit, did a special move underscore UI to return 32-bit. I think you can get rid of this by just not emitting that instruction. And overall it's similar, just a bit shorter here because you don't have to load the constant from the global memory. Like you are shifting by 1 and here you're shifting by 4. You just use the immediate constants. And for multiplication, it's 3 instructions. You load your constant, you move, because it's 3 operand version, you move save register somewhere and just do unsigned multiplication here. So that's how it looks like, and it's just write once. Yes, in some cases you need two different implementations, but it works everywhere. Usually it works everywhere. So yeah, I'm running a bit of time, but because just by the way, all graphs were drawn using Lua and Graphies. That's why I have so many graphs, because it's so easy to draw. And I did all this just in 2 evenings, I think. All right, I can switch back to this mode. So yeah, BPF optimizations. It's running in the kernel, and you need to be more paranoid about doing optimizations in the kernel. So what I do, I assume that BPF program coming from the user space is already optimized. Like for example, if it's coming from libpcap library, then it's already optimized. And for example, if I look at some particular program and I see it's moving value between A and X register 10 times, and you see in the end it's just a single move, so I don't do it because this can be done in user space. So you just don't do it. Don't move stuff unnecessarily. And I have some exceptions, but they come when I need something and they come for free. Or mostly free, then I add those optimizations. And unreachable instructions is a natural step when you do like initial flow analysis. It's a natural step to see whether this instruction is reachable or not. But in a normal program, you don't see unreachable instructions, so they should be optimized. And also, A and X might be used uninitialized, and in those cases, I set them to 0. But actually, if you don't initialize them explicitly in your filter program, the kernel will not accept them because they will fail a validation step. But yeah, you don't have to do it, but I still do it as a safety net, and because I'm not limited to NetBSD, where BPF validate does this. And I do fixed number of passes through the filter program to prevent any, infinite iterations trying to find an optimal solution. Just fixed number of passes, and that's it. So yeah, I implement trivial hints, and I think everyone else implements trivial hints. Like if X is not available, is not used anywhere in your program, then don't use it, and you will save some instructions in prologue, epilogue of a generated function. Find use before init. Again, they will not. If you use before init, then those programs will not pass validation, but I still do it. Jump. And I have array bound. The main optimization is array bound check elimination, and I do it in 2 passes. I don't have time to explain it in details, but I'll show you the results. So it applies to packet reads. And because filter programs often read bytes in decreasing offsets, you can save some, optimize away some checks by just checking the like if it's going to read a packet at offset 24, a byte at offset 23 anyway, then you can just check it at the beginning. And yeah, again, this one is not very visible. I can zoom in. Oops. So yeah, basically it needs 14 packet, 14 bytes, and this one needs 24, and I can just move it to the check here, and don't do this check at all. And actually, so this is, it needs 14 bytes, 24, 22, 15, and some unknown offset. But basically, it's just you can do single check here, 24. Is it 24 or more? Then go there. Otherwise, it's too short. Go just straight to return 0, and you just have some additional check here. And I think that's the two checks you have, like one check here and only one instead of two checks here, and no checks for this. So you eliminated actually 4 checks, 1 here and 3 of those. That's just what my optimization does, and I implemented it in Lua. That's why you. So I don't have time to explain you about execution trees and how my algorithm works, but basically, now I need to tell you one thing is actually this when you look at this. Right, okay, I'm running out of time. They always fall back to return 0, and there are no reads at all in this branch. And does it mean you need to disable your optimization? Like, because in one path it's 24, but in the other path it's just 0. But because because loads at high offsets are not return 0 anyway, and there are no side effects in BPF programs, you can just assume that instead of return 0, you can say load packet byte at, or in this case it's a word, at infinite offset. Well, in reality it's uint32 max plus 4, but it's high enough and higher than any real offset, because this load is indistinguishable. It will return 0 anyway, and yeah, it was previously return 0. Now it's just load at this ridiculous offset because they both return 0 and there are no side effects. And yeah, that's what you have in the end. Just check here and one check here instead of 2, and all those are optimized away. And if you change this to return 0 here instead of use short max, the whole program would collapse. But I don't do this optimization. And like if this was a part of a bigger program, then I could apply some optimizations to the other part, because like if this program uses, like this fragment uses some stuff, but this one doesn't, I can just just take advantage of it. But this is not just, you don't see it in real programs that just they are not unreachable code in real BPF programs which you receive from user space. And yeah, I think I don't have time for future optimizations, but and for above stuff and for testing, yeah, I use ramp for testing. It's very modular, and just like every time I add a feature, I just runs it through the tests, and it tests both user space and kernel. And there are some differences in the kernel because they are mbuffs and mbuff chains, and they're a bit different to work with. So yeah, that's it.
Thank you. Any questions?
Yeah. All right.
How easy is it to add new architecture support to?
Well, Taylor was done by one person. I think it should be quite straightforward, and yeah, it will take some time, and you need someone who is skilled to know enough about the architecture. Well, I think you can just read the instruction format and ABI specs and do it, even if you don't have enough skills. But it's just.
May I try to answer?
Yeah.
I actually looked at adding Spark 64 support,
Right.
and it's like 500 lines of code to do, but I didn't come around to do it.
Yeah, and Dalton doesn't have. I asked him. He doesn't have time and he doesn't have hardware. But I told him hardware shouldn't be a problem. You know, if you want to work on Spark 64, we can donate you hardware.
I definitely have it on my to-do list, but it's not an empty list. Any other questions? Okay. Thank you.